is occurring. So let's talk a little bit more about what equilibrium means and some other ways to view what an equilibrium is. So, for instance, if you've ever taken a physics class, you might have used these things called force tables. A force table is a round table in which you can put some weights, some masses at different points, and they're all connected in the center of the table to a central point. Well, you could have a force table in the state of equilibrium if you put three equal forces, F1 equals F2 equals F3, at exactly 120-degree angles apart, that you would divide the circle into three equal pieces. That would mean that all the forces are balanced. The central point wouldn't move. The central point would be in a state of equilibrium. That's a physical analogy for what equilibrium is. This diagram here represents a sort of equilibrium in which the dipole pulling in this direction in a CO2 molecule is equal to the dipole pulling in this direction. So the net, the sum of those two forces is zero. There's no net movement, so to speak, of the electrons. It's a non-polar molecule. That is another sort of system or a molecule in a state of equilibrium. But it's important for you to keep in mind that equilibrium is dynamic. It means there's still movement going on. It doesn't mean everything stops. There's still something going on. It's just moving in equal and opposite directions. So let's also imagine you have a beaker of water that's open to the environment. Well, we all know that the beaker of water would eventually evaporate. So that is not an equilibrium system. You would write just an arrow to the right. Water, liquid water gives you water in the gas phase. There's no backward reaction because there's no way for the gaseous molecules to come back into the liquid state. They just float away into the atmosphere. So you have to have, for chemical equilibrium, you have to have some certain constraints on the system. Usually that means you have to have it in a closed vessel of some sort. So let's imagine we'll take that same beaker of water, but we'll close it. We'll make it so that the water molecules can't escape. Well, if you did that and left a little space for the gas molecules to occupy, you would not completely fill up the container with water, but you would seal it. You would have eventually a state of equilibrium achieved. The rate at which the liquid water molecules would evaporate would eventually become equal to the rate at which the gas molecules condense into the liquid state. And that's the key. The rates are equal. The rate of the forward is equal to the rate of the reverse. That is what we call equilibrium. So the state at which the rate of the forward equals the rate of the reverse, we do call an equilibrium. At this point, no more measurable or observable changes in the system can be noted. So one way to graphically represent that is to show you that we can illustrate that with this diagram here. How are kinetics, which are the rates of reaction, related to equilibrium? Remember when we talked about kinetics, all we were really concerned about was how fast does a reaction occur from reactants to products. So what's going on in an equilibrium is as a reaction starts, the forward reaction will eventually slow down because reactants are consumed. As the reactants are consumed, the numbers of reactant molecules is decreasing, so they're going to run into each other with less frequency, so the rate at which they form products is going to eventually slow down. That's what you're seeing here in this blue line here. Well, as the reaction goes from time zero, as products start to form, eventually the amount of products that's present gets large enough that they can actually go back and break apart and become reactants. That's the reverse reaction. And that will eventually slow down as well. And when that comes to the same point at which the forward reaction is occurring, when they're equal, that is a state of equilibrium. But again, it's very important to remember that this does not mean that the concentration of the reactants. Remember, we represent concentration with these square brackets. That means moles per liter. Equilibrium does not mean that reactants concentration is equal to the product's concentration. A chemical equilibrium can favor reactants or products. We say it can lie to the right or it can lie to the left. So concentration doesn't change with time. It means it doesn't change with time. So let's go back to this expression here and talk a little bit about how we mathematically represent what an equilibrium constant is. So let's just take some generic reaction. You know, we like to do that. We'll just represent things in general. So let's just say you have two reactants, A and B. They are going to form some products, C and D, and they develop an equilibrium, double-headed arrow, forward, backward. How do we represent that situation? Well, we have a capital K that we use, not a lowercase k, capital K. That represents equilibrium constant. It's equal to it's defined as the concentration of the products divided by the concentration of the reactants. So in this case, we would write the molar concentration of C times the molar concentration of D divided by the molar concentration of A times the molar concentration of B, where these brackets again mean moles per liter. And here's some different ways to represent molarity. You can write it out like this, or here's an abbreviation. Sometimes we just use a capital M. In this case, this would be the molarity of component C, capital M subscript C. Now, if we don't stress our equilibrium, that is, we keep the temperature constant, if we don't stress our system, I should say, it will eventually come to an equilibrium state, and you can have three possible situations. Maybe I should keep that down here just for a little bit. Okay, here. So, again, let's say you start the reaction at time 0. So that means no matter what state of equilibrium we do end up in, we have 0 concentration of products. They haven't formed yet. So as time goes on, in any possible situation, the reactants are always going to decrease and the products are going to increase. But the products can increase to a level that's not always the same, and the reactants can decrease to a point that's not always the same, depending on what reaction you're talking about. So if you have the situation in which the reactants are present at equilibrium in a larger amount than the products, that's this situation here, we say that that equilibrium constant, KEQ, is less than 1. If you have a situation in which the reactants and products concentration comes to be when they're equal, then you have a equilibrium expression K equal to 1. Those aren't really common, but they do exist. These two are by far the more common possible situations that do arise in reactions. In this case on the right, what happens is the products are forming much quicker than the reactants are being consumed. So you end up, when you do finally reach equilibrium, the amount of products present is much larger than the amount of reactants present. In that case, we have a KEQ that is greater than 1. But in all three cases, what's been achieved at this point, the change in concentration with time, is constant. It's a horizontal line. That is a constant rate, we say. So the rate of the forward equals the rate of the reverse reaction. And we're going to talk about a little bit about each particular situation. Since I've given you this generic expression here for K, let's talk about a few specific examples. What does it mean? How do we write these expressions? So let's take this process here. This is every general chemistry textbook uses this expression, this particular equilibrium. It's called the Haber process. It was invented, well, it wasn't invented, but it was perfected by a scientist whose name was Fritz Haber. He was he was like the Dr. Evil character in the Austin Powers movies. He was a brilliant scientist, but he was I don't know, he got caught up with some bad people. He basically used his chemical knowledge to do some very bad things. He was in the World War I. He actually helped the German army develop chemical weapons. They used chlorine gas on people. He was responsible for some of his inventions. Eventually led to what's called Zyklon B gas, real nasty stuff. But he eventually fled Germany when the Nazi Party came into power. But he was actually, known as a evil genius, so to speak, because he developed this process, where he developed chemical weapons. But this process here has revolutionized the farming industry, because it's essentially how we make fertilizers. So without his pioneering work, the farming industry would not be in the state it is today. So he did good and bad things. But this process here looks like a simple equilibrium. You take nitrogen gas from the air, you react it with hydrogen, 3 moles of hydrogen, you can get 2 moles of ammonia gas. So this is how we write an equilibrium expression. We take the product concentrations and divide it by the reactant concentrations. So in this case, we have you always have to have a balanced reaction, keep that in mind. So we have ammonia molecules, the molarity of them raised to the second power, divided by the concentration of nitrogen to the first power, because there's a 1 in the balanced reaction in front, and the other reactant is hydrogen to the third power, because there's a 3 in front. We call that more commonly K sub C, because it's an equilibrium constant written using molar concentrations. But if you just call it a K or KEQ, that's fine too. The other way to write a KEQ expression is when you have gas molecules, when they're all gases, we can measure the pressure of the gases. So this version of the equilibrium constant looks similar in that the pressures are raised to the same powers as the molarities are, but we're using pressure. And that's a special type of equilibrium constant called K sub P. And they're not always equal, but they mean the same thing. It's either going to be a value of K less than 1, equal to 1, or greater than 1. We won't go into what that one's equal to right now, because it does depend on temperature. But the Haber process, this process has been perfected in industry for making ammonia, which is a precursor to many other different types of fertilizers. And you can actually use just pure ammonia gas as a fertilizer as well. So what about the size of KEQ? What does that mean? Well, sometimes KEQ is much larger than 1. So I have a little picture here to show you what that represents. Here's a reaction in which you have a very large equilibrium constant. This reaction is another gas phase reaction. Nitric oxide reacts with ozone gas to give you NO2 and oxygen gas. Again, this could be a reaction that is occurring in the upper atmosphere. But you can see when we measure K at a certain temperature, it's a huge number, 6 with 34 zeros. What does that mean? It means that at equilibrium you have essentially 100% of products and almost none, none of these. So I represented that visually with this picture over here. You'd have very few of the reactant molecules, and you'd have a very large number of the product molecules. The other situation you can have is when KEQ is much less than 1 or less than 1. This would be an example of that situation. Calcium carbonate, solid calcium carbonate, which is just limestone or marble, can dissolve in water to give you calcium ions and carbonate ions. Well, that has a very small equilibrium constant, 3.8 times 10 to the minus 9. What that means is if you had and notice that these equilibrium situations are all represented here in closed circles. That means they are not open to the atmosphere. They're not open so that gases can get out. They're trapped within a closed system. Well, if you had calcium carbonate solid and dissolved it in water, the fact that K is very small, what that means to us is that we'd have mostly solid calcium carbonate sitting on the bottom of our reaction vessel, and very, very few ions of calcium ions and carbonate ions, and mostly water. This makes sense because marble statues can withstand rain for hundreds of years. This is the reaction that would occur if marble is going to break down in water. So since we know that the marble statues can last for hundreds of years, it means that this is a very unlikely reaction to occur. And we represent the K. Notice how we write the value or the expression for this. The K of this reaction is just the product of the calcium ions times the carbonate ions. There's no value. We don't use, or we don't plug in the concentration of calcium carbonate solid. There's no solids in a KQ expression. The reason why is because it doesn't make sense to really say the concentration of a solid. The concentration of a solid is constant. It's the same thing as saying what's the concentration of pure water. It does have a number, but to us, we're just going to think of it as a constant. It's so large, the concentration of these solids and liquids is so large that it essentially is constant and it doesn't change. What we're putting into these equilibrium expressions are things that can change with time, either gases or aqueous substances. So we'll end this video here, and in the next video we will continue our discussion with equilibrium, talking about Le Chatelier's principle.